So we just got done talking about a heating curve so that we can see that there are, if you do a full-blown heating curve from solid all the way to gas, there are 5 different parts to it. The diagonals are where you're increasing the temperature, so what's happening, kinetic energy is going up, which means motion is changing, but potential energy is not, so we're not breaking any IMFAs along those diagonals. At the plateaus, however, kinetic energy now becomes constant because this is where we are breaking IMFAs. So in a heating curve, we're adding energy. We're either adding kinetic energy at a diagonal, potential energy at a plateau, but we're constantly adding energy. So down here, there's less energy of both kinds for the material, and over here, there's more energy of both kinds for the material. We are adding energy, so we're breaking bonds. If you take a look at the cooling curve, which you have a little version of the cooling curve. A cooling curve obviously is the opposite. We're going to take and start with a gas and cool it all the way down to a solid. So what's happening, temperature is decreasing over time, which means we're not increasing, we're removing. So kinetic energy is going down, or potential energy is going down. Motion is slowing. And as motion slows, what happens? We can form IMFAs. So these two feed off each other. As the motion slows down, more IMFAs form. As IMFAs form, motion is forced to slow down even more, and so on and so forth. So really the only difference between a heating curve and a cooling curve is that you are adding energy to a heating curve. You're removing energy from a cooling curve. So this is an endothermic process. This is an exothermic process because this material is losing energy. We are breaking bonds in a heating curve. We're forming bonds in a cooling curve. We're increasing motion in a heating curve. We're decreasing motion in a cooling curve. So everything's the same but opposite. All right, so with that being said, let's take a look at a problem so that you know how to handle doing one of these. So here's a question. How much energy will it take to raise the temperature of 80 grams of trichloromethane, CH3, from 0 degrees to 100 degrees? So when you answer one of these questions, what I want you to do is a couple things. I don't want you to just do calculations. I want you to draw a very quick sketch of a heating or a cooling curve. So in this case, we're heating it, so we're starting at 0 degrees, and we're going to 100 degrees, okay? So we want to show the two endpoints. How many different parts am I passing through? Remember that we have 5 different constants that we may have to use, but do I really need to? That's where knowing the melting point and the boiling point comes in. Trichloromethane melts at negative 63 degrees Celsius. We're already above that temperature because we're starting at 0. So we're not starting with any solid. So we don't need to use this value because we don't have a solid. We also don't need to use the heat of fusion because we're not going to be melting it. It's already melted. It's at 0 degrees. Trichloromethane is already a liquid. So really, what am I doing? I'm in liquid form. I'm going to increase the temperature until where? Boiling point is at 62. So I'm going to mark that temperature. So I'm going to increase from 0 to 62. Then I'm going to boil the trichloromethane. And then I'm going to raise the temperature to 100. So in this particular question, there are only 3 calculations that I have to go through. So again, if you want to call them Q1, Q2, Q3, you can do that to keep yourself straight. Okay? So typically, I'll give you all the pieces of information, and you have to figure out, do I need to use them all or not? So drawing a quick diagram, notice it's not to scale by any means, but drawing a quick diagram lets me figure out what's going on. All right, so now if I do my calculations, first calculation, second calculation, third calculation, add them all together. Okay, so for Q1, what am I doing? I'm increasing the temperature of the liquid, so I have to use the specific heat of the liquid. MC delta T is going to be 80 grams times the specific heat is 0.98 joules per gram degree Celsius. And what's my delta T? 0 to 62 is 62 degrees Celsius. So if I do that calculation, I wind up with, hold on, let me look at my cheat sheet answers. I wind up with 4,861 joules. Okay? So then Q2 is going to be boiling the trichloromethane. So I'm going to be using M delta H of vaporization. I don't need to worry about a delta T because there's no temp change. So I still have that 80 grams, but now my heat of vaporization is 31.27. Now look at units, kilojoules per mole. These units aren't going to cancel out, so I need to be careful. I have to make sure that I use molar mass. So if I look up molar mass, I know that 1 mole weighs 119 grams, 19.5 grams, sorry. And if I get an answer, it's going to be in kilojoules. This is in joules. So I'm going to do one more quick conversion and change it into joules. So my Q2 can be added to my Q3, and I wind up with 20,934 joules. A state change is usually always more energy than simply increasing the temperature of something, because breaking bonds is a lot more energy involved than just making a molecule move a little bit more. All right, so Q2, I'm at the end of that plateau. Now I've got to heat my gas. So Q3 is going to be, again, heating the gas, MC delta T of the gas. Still those 80 grams, but my gas is 0.56 joules per gram degree Celsius. My delta T is now 62 up to 100, so I've got 38 degrees here. And that's going to give me joules, which is what the other two are, so I don't have to do any additional work. That means I'm going to have another 1702 joules used to do this step 3. So then overall, how much of the energy is it going to take? It's simply Q1 plus Q2 plus Q3. So I've got 4861 plus 2934 plus 1702. I'm not rounding off yet. I'm going to wait till the end. If I look at all these numbers, technically, oh, that's really bad. I only have one digit there. So sig figs aren't too good here, but this is way more sig figs than I should have. So if I add those all up, I wind up with 27,497 joules. So practically, I probably want to round it off to either 27,000 or 27,500. I definitely don't want to go more than that, because accuracy is pretty bad up here. So let's say that I got more sig figs even than I should have, but at least 27,500 is a little bit better. So each step individually, and then just add them all together. But again, what I want you to do is get into the habit of drawing a heating or a cooling curve, because that's going to let you see how many calculations you have to actually go through. And if you don't need a portion, don't draw it on the graph. Just mark the important temperatures that you need. Again, we've got time here. I probably should have done that before. I got temperature here, degrees Celsius. And that's how you do a heating and cooling curve calculation.